Hello students. Today the topic of our discussion is Communication Theory 19 EC 403, under which we will focus on Unit 4 today. So let us quickly go through the course outcome of Unit 4. So we'll compare the noise performance of amplitude modulation and frequency modulation systems here. So in today's class, we'll focus on the noise analysis of both AM system as well as FM systems, where we take into account various noise parameters like signal to noise ratio and the figure of merit of AM and FM system. Yes. So whenever we talk about noise, we need to care about two different parameters. One is the channel performance, the other one is the receiver performance. So as you design the channel, we assume that the communication channel of any system is noise free, or it should be distortionless. But however, we need to take into account the noise factor, where we model our noise as an additive white Gaussian noise, which is known as AWGN noise, which is additive white Gaussian noise. Also, the receiver model is designed by assuming that we have an ideal bandpass filter followed by an ideal demodulator section. So we assume it to be an ideal case in order to minimize the effect of channel noise. So the diagram represents the receiver model, where you have ideal characteristics for both bandpass filter as well as the demodulator section. And here this represents the graphical waveform for ideal characteristics, where the power spectral density is N0 by 2. Since we assume it is additive white Gaussian noise, the power spectral density for the white noise is always N0 by 2. Yes, so here comes the most important noise parameter, which is signal to noise ratio. So whenever we study the signal to noise ratio for any system, we'll be able to know how much amount of noise is being involved into our receiver system. So we prefer the ratio of signal to noise to be maximum always, in order to have a better performance or effective performance of any kind of receiver system. And this signal to noise ratio serves as the best criteria to measure the noise performance for both AM as well as our FM system. So let us now define what is this SNR. So the signal to noise ratio is defined as the ratio between the average power of the message at the receiver output to the average power of noise at the receiver output. So the one more parameter which decides the performance of any receiver system is its figure of merit. So where we take into account the signal to noise ratio at the output as well as at the input. So the ratio between the signal to noise ratio at the output of our system to the signal to noise ratio at the input of the system is defined by its figure of merit. So now with the help of these two parameters, let us move on to analyze the performance in case of a double sideband suppressed carrier receiver system. So hope we might have learned already the concepts of DSB, SE, AM in the previous units, as well as single sideband suppressed carrier system in your previous amplitude modulation topics, right? So here this diagram represents the coherent detection or coherent demodulation of a double sideband suppressed carrier AM receiver. And this system has the property where the input message component is unmutilated, or it is actually carrying the noise component additively. So we say that the noise component always appears along the input message additively, irrespective of the coherent detection, where we try to suppress the interference of noise. We do have some noise components to be added. So this is the equation which represents the double sideband suppressed carrier. So the first factor AC gives the amplitude, the carrier A suffix C, then you have the message component M of T here. So here we say that the carrier frequency is always greater than the message signal bandwidth W. And we try to represent the normalized or the average power as S of T, which is AC square into P divided by 2. And here P represents the average power of your message signal. So now once again we try to calculate the average noise power. So we try to calculate the average noise power by taking the product between the bandwidth and the power spectral density. So since here we have assumed the noise to be additive white Gaussian noise, the power spectral density stands as N0 divided by 2, and we all know the bandwidth is twice it of the highest frequency, which is 2 FM. So the average noise power is 2 FM into N0 divided by 2. So when we just take the product between these two parameters, we get the average noise power as FM into N0. So now we quickly move on to calculate the total amount of signal which is present at the cocurrent detector. So it is the sum between the signal plus noise component. So when we talk about the noise component here, we incur or we come across two different types of noise components, which is the in-phase component as well as the quadrature component. So after passing the signal through an low-pass filter, we try to eliminate some amount of high-frequency noise components from the signal, which finally leads to the receiver output. So this y of t, so this equation gives the output of our low-pass filter where we get the received signal. And from this equation, we are able to learn that the message and the in-phase noise component appears additively at the receiver end. So this is the in-phase noise component and this is your message component. And when we talk about the quadrature component, it is completely eliminated by our coherent detector. So the output of my double sideband suppressed carrier AM receiver has the message component, which is added additively along with the in-phase noise component. And with the help of the signal to noise ratio, which is measured at both the input section as well as at the output section, we calculate the figure of merit and we get it as to be unity here. So in case of DSB SE receivers, the figure of merit stands as 1. Similarly, we also analyze the noise performance in case of single sideband AM receivers, and this is the equation which is representing the modulated SSB wave. So here you have your message signal component M of T as well as, and this component represents your Hilbert transform of your message signal component. And once again, we consider the noise as additive white Gaussian noise, and of course we need to calculate both the in-phase as well as the effect of quadrature components here. And when we observe or analyze this equation, we find that these two components, M of T as well as the M cap of T, which is the Hilbert transform of the original message signal, are found to be uncorrelated between each other. So I say that the power spectral density will be always additive here. And we, as how we did for the previous system, we try to calculate the average power for both in-phase as well as the quadrature component. So it is once again AC square into P divided by 4. So I calculate both the in-phase as well as the quadrature phase here. And the power spectral density of the additive white Gaussian noise system is always N0 divided by 2. And finally, we try to pass the signal through a low pass filter and we try to get back the received output at the SSB coherent receiver. And this equation represents the final output where we have the message signal component along with the in-phase noise component and the quadrature component. So we say that from this output equation, I'm able to observe that the Hilbert transform of my original message has been eliminated. But however, I have the effect of both in-phase component of noise as well as the quadrature component of noise. And once again, with the help of the signal to noise ratio parameter, I try to calculate what is the figure of merit both at the input as well as at the output sections, and it is found to be 1 here. Yes. So this is just a summary section. So now we'll move on to the performance of noise in case of FM receiver section. So in case of FM receiver, once again, I go for the demodulator part. And here, normally, in case of frequency modulation, only the carrier frequency is changed and the amplitude of your frequency modulated wave is supposed to remain as constant, right? But however, due to the presence of noise, the amplitude also tends to change here. So in order to avoid this amplitude variation, we try to introduce a limiter after the bandpass filter. This limiter actually helps us to remove the modulated waveform or the variations in the amplitude at the output of bandpass filter. Yes. So we try to analyze our FM discriminator circuit, which is having a slope network, which is a purely reactive transfer function as well as an envelope detector. So when we observe the output, we have the inclusion of narrowband noise at the bandpass filter output, and this is the equation which is representing the narrowband noise. And this equation here represents the total signal power and finally we also analyze the output at the envelope detector, and the variations in the envelope of our input signal is removed with the help of a limiter section. But however, our main objective is to eradicate the error which is instantaneous, which is caused mainly due to the presence of this narrow band noise. And then we try to calculate the noise component at the output of my FM receiver. And with the help of appropriate filter deployment, we try to remove the effect of noise at the FM receiver section. So the noise power is denoted actually by the notation ND of T, and this is obtained by passing our quadrature component through a linear filter. And then we also calculate the signal to noise ratio at the input section as well as at the output section, and knowing the value of signal to noise ratio at the input and the output, we try to measure what is the figure of merit of the system. So the figure of merit of a wideband FM system is a quadratic representation of the deviation ratio. So when the carrier to noise ratio is very high, there's an increase in the transmission bandwidth, and this provides a corresponding quadratic relation or an increase in output SNR. So this is the inference we get from the measurement of figure of merit of a narrowband FM system. So this slide represents the effect of capture effect. In case of capture effect, we try to measure what is the relation between, or what is the effect of noise interference. Whenever the interference of noise signal is very much stronger, our FM system locks to the stronger signal and it suppresses the weaker signal. When our FM input is of equal strength to that of our noise signal, the FM receiver starts to fluctuate now. So this fluctuates back and forth in order to decide upon the stronger channel, and this phenomenon results in capture effect. So this is actually defined as the inherent ability of any FM receiver system to minimize the effect of unwanted signal noise at the receiver. Thank you.